In this part of the lecture, the examples that I'm going to give will be more geared towards industrial engineering. Now, the examples that I gave was just to show how complex certain systems can be, but the examples that I'm going to give from this point on will be from the topics that we are going to see in the next 2 or 3 years in the IE curriculum. Okay, so let's start with the one daily example. Now, most of you probably are familiar with automobiles, more than I do probably. And so the one thing that we always read about automobiles is that there is this so-called technical efficiency, if you recall. When you buy a car, they say that this is the ideal speed that you should drive the car, because when you drive the car at that speed, the average per mile or per kilometer consumption of gas is the best. Okay, so they have designed a certain engine which is going to have its lowest at that point when you are driving a car. So this is called technical efficiency. So does this mean that you have to drive at that speed all the time? Or are you going to approach that speed? So that speed is usually 90 kilometers per hour. Okay? So it means that if you are driving within the city, you have to go a little bit faster. The limit is 70 or 50 in most of the places. But no, we don't do that, of course. Or we try to do that up to a certain extent. But the idea is that I am an engineer who designed that. My perfect vision of the world tells me that this is the best engine that you can find around. But with respect to fuel consumption, the best speed to drive the automobile is this level. Now, on the other hand, when you look at a little bit outside the perspective of that brilliant engineer, you're going to see that the other things that will affect the economics of driving automobile is much different. So we might be saving 1 or 2 or 3 Turkish liras per liter if we drive at that speed. But we might be losing from other things. And that's basically, it is basically, the automobiles are driven in systems that are not independent of where we live. If everybody was driving in a track independently, the efficiency concerns, the technical efficiency concern of the engineer would be able to come true. But unfortunately, we are all driving in an environment where certain roads are limited, certain other roads are not limited, but you have population all around. It's always crowded. And so in that respect, okay, this economic efficiency versus technical efficiency is not necessarily going to coincide. Now, should an engine manufacturer or should that engineer only think about the economic efficiency in general? Of course not. But when we are dealing with the solution of this problem, let's say that we are trying to minimize the total cost that these automobiles are creating when we are driving them, the concern is not only going to be the efficiency of the engine, but there are other concerns that we have to take into account. This is what we call systems approach, actually. Okay? So you look at the system before you make decisions. Okay? So this is one example. And of course, what we mean by economic efficiency will be made clear in the next slide. So usually what we have is we have the so-called technical efficiency, which we defined up to this point as efficiency. And then we have economic efficiency, which can be used synonymous to effectiveness. So I have designed a very good engine that if you go with 90 kilometers per hour, the energy consumption will be 55% less than what we are doing now. This is very good improvement, am I right? But basically, when you take that into the traffic system and examine the role of that automobile within the traffic system, things are going to be different. Okay, now similar thing is going on with the electric vehicles that has been manufactured all around. You know, electric vehicles are very good for the environment because they consume less oil. Of course, they are using other sources of energy, which might still be debatable, but there are a number of issues, and the issues that are raised is not only technical efficiency in the case of electric cars. So this is actually important to understand. And what the systems thinking idea is basically take efficiency, effectiveness and efficiency into consideration at the same time. So that's more or less the idea. Okay, now let me give an example. Let me give a hospital example. Now we have a lot of IEs working in hospitals. Hospitals are formed, they have different departments in hospitals, so different departments. And usually the current understanding is that we analyze hospitals with respect to their performance in each department. That's the usual way of doing things. For example, you have this brain department. So they look at the number of patients come and try to analyze the effectiveness of that department with respect to other departments. Now, let's consider one example. Let's say that we have a testing department where we send our blood samples and test the blood sample. And then we have the blood bank, which is going to be used when somebody needs blood. Okay, now what happens is that, for example, before certain surgeries, you talk about a certain amount of blood that's needed for the surgery. Okay? Now, in the testing, on the other hand, what happens is that you simply take the sample that you are given and you examine that. Now, the testing, let's say the following case is happening, which is usually the case. The testing department is very efficient in its operation. So, for example, every time that a blood sample comes, they can get the results in 10 minutes with very low cost, very efficient operation. The blood bank which is basically responsible for obtaining blood in the correct amounts and with the correct quality, so there is a relation with testing, and make it available before the surgeries, okay? And it may work very efficiently. Okay, in the coming years, you're going to see that blood banks are actually not very much different than manavs, actually, produce shops in Turkey, because the blood is perishable, and apple is also perishable, and it's the same logic that makes them you can use similar logic in storing the amount of different types of blood. Okay, so basically it is an inventory problem. So let's say that you operate that very efficiently. Now, the only thing which is missing here is that somebody so a doctor, medical doctor, is ordering a request for a certain test. And according to the results of that test, the blood quantity is determined. But there are a number of different tests that can be asked, depending on different situations. Now, it turns out that if you ask for wrong tests, okay, you are going to basically make the following error. At the time of an operation, you will need probably more or less blood. Okay? So basically the initial information that comes about the quantity of blood that's needed is going to be very different if you ask for wrong tests. Now, if you analyze, for example, this situation, this is working very efficiently. This is working very efficiently, given that the tests are correct, of course. But it turns out that if a group of medical doctors is continuously asking for improper tests, okay, then regardless whether your system is very efficient technically, okay, it's not going to be effective. Because basically you would either be carrying too much blood or very little blood in certain circumstances, so you will always need emergency blood, or you will probably send certain tests to outside sources. But internally, given the orders that they receive, they might be doing things very efficiently. So this is one good example why we should have systemic view. As an industrial engineer, you go to this department and see that they are doing everything perfectly. They are using models, mathematical models to solve their problems, and everything seems to be perfect. But what is wrong is basically the input that comes from the medical doctor or group of medical doctors. Now, unless you find that problem out, you won't be able to solve the system's problem. Individual parts are very good. Now, our role as IEs are, we have to make sure that the blood bank operates efficiently, of course, but not only that, we have to make sure that the system actually operates efficiently in this case. Otherwise, our efforts are not going to make much sense. So this is actually one example. Any questions on this example? Now, let me give another example. Okay, and that example comes from spare parts. Now, think about the company, mini company that we watched the video of. Think about certain machinery that you have seen. I think the largest equipment that we have seen was the metal forming part. The form of the automobiles was coming out. There were like big presses which were obtaining those metal forms. Now, those presses they are called press. It's very similar in Turkish. It's the same thing. So what happens is that they are heavy-duty equipment, and when they actually operate like this, usually you have some metal here, and when you have enough pressure on that metal, it will take the shape that you want it to take. Okay, so it's called metal forming, actually. So basically, let's consider that machine only. Now, if you go to Mini, you're going to see that at some part of the inventory of Mini, they will have some parts which are full of dust, actually. And when you ask them what are they for, they will say that they are the spare parts for spare parts for the press. Okay? Now you're going to say, why are they so dusty? So it is obvious that you have not used it for 25 years. Okay? It's so dusty there. Okay? So this is basically something that we always have in manufacturing environments. Now, we need those spare parts because what happens if something wrong, a part of that machine breaks down? Now, the part that may break down might be small, large, but you might have this whole colossal part that comes and obtains the pressure is broken. Now, you have to stop manufacturing of that. Now, how are you going to manage that? Now, how long will it take for you to replace it? Okay, so in order to make sure that we may have those extreme cases, which is probably the probability of that machine breaking down is probably less than 0.01%, that part of the machine. But you still have a spare part for that. Because when it breaks down, it will probably take at least 20-25 days or a month before you can start doing production again. Now think about what will happen to Mini if they don't produce those parts for a month. The cost is unbelievable. They will sell 10% less automobiles that year, just because of one machine. So what we do is we keep some spare parts. But keeping spare parts is not cheap, because keeping spare parts means that you have another equipment sitting idle there, and that equipment is probably going to cost you, I don't know how much, but $3 million. So you let $3 million sit there for just in case use, and you let it sit there for a long time. Now, the main concern here is, of course, operation. Now, as IEs, our role is not to accept that they should sit there. We should examine the speed that we can obtain this part from another source. Or we might do this in another way. I might have stock for the parts that are manufactured by that equipment sitting idle. You can either do that or have a spare part for the press sit there. So there are a number of choices. So when you look at purely from efficiency point of view, there is no meaning of this. You are not going to keep that. So if you are a person who will come there and say, these are dusty, they have never been used at all, so let's get rid of them. Okay? But basically, it turns out that it might have a function, and the only way to answer the question is to analyze the system as a whole. Okay? So this is another thing, and of course, in both cases, you're going to see a number of courses, how we can deal with these type of issues, if we can, of course. Okay. Now, so basically, this is what I want to say. Now, let me use the board and give you another example. This time, the example will be a numeric example, and you will probably see how we should approach to certain type of problems. Now, I'm going to call this as the unexpected outcome. But unexpected outcome might be the correct outcome, even if we cannot give a straightforward logic to it in the first place. Now, I'm going to consider a simple production example. Very simple. And I'm going to give the data of the problem. Now, in production, let's say that you have a certain facility, and you are producing more than one product at the same time. Okay? And in general, our understanding is that we usually look at the profit margin of products and try to make decisions according to the profit margin of each product. Now, what is the profit margin? Profit margin is the profit that we obtain if we sell each product. Okay? And I'm going to divide it to the selling price of the product and multiply it with 100. This is the definition of profit margin. Okay? So profit that you are going to obtain, profit means selling price minus all the costs that are associated with manufacturing that item. So the remaining part is the profit. Okay? So divided by the selling price, which shows the relative value, actually. Because if you have multiple products, this is a good way of looking at at different things. This is what finance people would do when they are trying to buy shares. Okay, you look at the percentages that you are going to receive as benefits, because basically selling price is what you pay, and the profit is what you are going to receive later on. So you can buy 3 of it if it's very expensive. You can use all your money, but the return is what is important for you. So looking at this definition, you can say that if I am going to produce something, so it is generally accepted that business, okay, it's generally, it is a generally accepted business principle to push for highest for products, excuse me, with highest profit margin. And this is in general a true statement, in general, of course. Now looking at this, so in our production example, I'm going to supply you some data, and according to that data, we will apply this business principle. But of course, our case will be a little bit more complicated than the general environment. And because of that, it's not going to be the best solution. Now, you can see what's coming up. Okay, so let me give you the example. Let's say that we have two products that we are producing. So we have product A and product B that we are producing. First, we have the raw material cost of the item. And let's say that product A is $50 per unit, and product B is $70 per unit. Okay, this is the raw material cost. And then I put both of them into an equipment that I have in my backyard, okay, which can operate 8 hours a day, and the cost that I'm paying for the operation is $20 per hour. Now, of course, this is the property of the machine. So let me actually write it inside the box. So production capacity is, this is what we call capacity. It's 8 hours per day, and we pay $20 per hour. Okay, so this is about the equipment. Now, I cannot, for one reason or another, I cannot operate more than 8 hours, let's say. Now, A is going to require 2 hours per unit of this machine, and B is going to require 1 hour per unit from this machine time. So A has another difficulty, so it takes a little bit more time. So raw material, I place the raw material to the machine, it processes, and then product A is going to come out. So as a result, the total cost of each A is going to be 50 plus 2 hour cost of 2 hours is what? 40. So this is going to be $90 per unit. And then B is going to be, again, 70 plus 2 hours. This time it's 1 hour per unit. So it will still be $90 per unit. So the cost is going to be very similar. Okay? Exactly the same. I shouldn't even say. So this is how I obtain a unit of A and B. Now, I'm also going to have the selling price. Now, as A takes more time to manufacture, probably has something tweaky in the design, so it sells for more. Okay? So we can sell this to $180 per unit, And the other one, we can sell it to $150 per unit. And moreover, of course, in order to make the problem realistic, I have the upper bound for demand. In other words, the total amount of quantity, the most quantity that you can sell. This is going to be 3 units for A and 4 units for B. Of course, these are daily number of units. Okay? Now, this is a simple example where there is the cost structure is the simplest possible cost structure that you can have. You're going to see that we will deal with more difficult cost structures, more difficult demand patterns, and so on. But this is a very simple sketch of a production problem. Okay. Now, how are we going to solve this problem? Using the idea of profit margin, of course. Now, let's compute the profit margins. Profit margin for A is going to be 90 divided by, 180 minus 90 divided by 180 times 100, which is going to be 50%. And profit margin for B is going to be 150 minus 90 divided by 150 times 100, and this is going to be 40%. So intuition tells us that the way that I'm going to decide on this is simply I will first fulfill the demand of A, because the profit margin of A is larger. And with the remaining capacity, I will fill up the demands for B as much as I can. So it means that I will have daily production will be 3 units of A. And how long will it take? 3 units of A? 6 hours. So I will have remaining 2 hours. And so this is going to be 2 units of B. Remaining 2 hours, I'm going to manufacture 2 units of B. As a result, my daily profit will be 3 times 90 plus 2 times 60, which is $390 per day. Okay, I mean, no trick. This is what we obtain. Now, of course, here, systems thinking, or actually critical thinking, will tell us the following, will make us investigate the following. Now, this is a performance measure, am I right? According to the discussions that we had throughout the semester, from the beginning of the semester. This is a performance measure. And the claim is this performance measure is going to give us the highest profit value. Now, that claim might be true in general, because that's what the business practice is telling us. But is it true for this case? Okay. Yes? It's not. So what can we do? What is the reason why it is not?
Another choice of producing 4 units B per day and 2 units A per day will get a high profit.
Okay. Will give us a high profit. Did you get the numbers? If we produce 4 units of B and 2 units of A, the profit will be higher. Okay, let's do that. Four units of B and 2 units of A. Okay, note that we are still using 8 hours worth of machine, so this is going to be 2 times 90 plus 4 times 60, which is going to be $440 per day. No, 420. Okay. Now, why is the reason for this? Well, there is something else that maybe we should think about. And that's the amount of capacity that each product utilizes. Our profit margin performance was a very simplistic performance. Why? Because it assumed that the amount of capacity that they use, limited capacity they use, is the same. Now, what if we define another measure, the profit that we are going to have per hour of the machine time? Okay, that's another measure. In other words, I am going to use the machine for an hour, and let me compute, instead of profit margin, let me compute each product's profit per unit hour of the machine time that I used. Is that possible to do? Maybe that will give me a better solution. And any other alternative that you can see which will be better? Any other alternative that you see which will be better? Okay. Now, hopefully, in 2 years' time, when you look at a problem like this, you're going to see that you don't have more than 2 alternatives for this problem. Yes?
8 units of B is high for.
Okay, if you have 8 units of B, okay, if you only produce 8 units of, but you can only sell 4 of them. Okay, so 8 units of B is not allowed. Okay, but that's not the best. It doesn't exist. Okay. So for this problem, actually, these are the 2 choices that we have for the numbers that are given. Anyway, but that's beyond what I want to do. So another alternative will be, why don't I look at the profit per capacity unit? Because as your friend suggested, this solution is much better. And it considers capacity first. It uses the item that uses the least capacity, fills up the demand with that, and then puts the remaining to the other product. Okay? So this is basically an approach which takes capacity into consideration. So let me then use the following logic, change the logic, and why don't I compute profit per capacity unit, or let's say profit per capacity. So in that case, what will be the profit per capacity for A? For A, the profit is 90, but we use 2 hours of the capacity. So this is going to be $45 per hour of capacity. Okay? Whereas B is going to be 60 divided by 1, so it will be $60 per hour as the capacity. Okay? So in this case, as your friend suggested, using this measure, I am going to have 4B, where 4 is the maximum demand that it has. So 4 times 60 plus 2 times 45 is, 2 times 90 is going to lead me to $120 per day profit. Okay. Now, let's think about this again. We have 2 measures. One of them is the profit margin idea, which seems to be very realistic, actually. If you have more profit margin, you may want to use your sources, your resources, to satisfy the demand with the largest profit margin. But when will that be true? If you have a lot of resources, and if you are not going to have any limitations with respect to demand and resources, this is what you would like to do, actually. But in our case, we have a limitation in the total resource, as well as a limitation in the total demand values. The demand values are also limited. So in that case, it seems that the new logic that your friend introduced will work much better in general. Am I right? Well, that's what it looks. It looks that this is what's going on. Now, what I will do is I'm going to change the parameters of the problem a little bit. The numbers used in the problem statement. Change parameters. For example, let us assume that let the selling price of A be $210 per unit. So I increase the profit of A a little bit more. I made A even more profitable. So according to the profit margin statement, instead of selling it to 180, now I'm selling it to 210. The remaining parameters are the same. Now, in that case, what will happen? In that case, the profit per capacity use of A is going to be 120 divided by 2, which is going to be exactly $60 per hour. Exactly the same as what it is for B. So they are identical. Okay. In that case, how are we going to select the production quantities? Are you following me? I just changed one of the numbers. Okay, so what is the best solution? Now they have exactly the same profit per capacity values. Okay, and, but of course their profit margins are still different. The profit margin of A is now even higher than what it was before. Okay, so what will be the best selection?
In the alternative, we can product 6 products, but in the first solution, we can product 5 products.
Okay, so?
We can find a solution like that.
Okay, so you want to maximize the number of units that you produce? Okay, well, the maximum number of units that you can produce will be 6. I can tell you that because you have the demand. If the demands are 4 and 3, you can produce 4 units of B and 2 units of A. That's the maximum number that you can produce. So you are now introducing another performance measure, if I'm not mistaken. You are suggesting that we should maximize the number of units that we produce. Okay? So, and that result is going to be 6, regardless of the profit or regardless of the profit margins or profit values of the products. Is that going to give the best profit solution all the time? Okay, let's organize to this case, to the new case that I wrote here. So the new case that I wrote here is I changed the numbers. So the selling price is 210. Let's concentrate on this. And the profit per capacity of A is identical to what is the profit per capacity of unit B. In this case, what is the solution that you want to select? Well, of course, we want to maximize our profits. Yes?
3 times A and 2 times B.
Okay, this time we are going to shift to the other one. So it means that your friend's logic was correct for the initial problem because this would give better solution. But now with these new parameters, the solution, you will not be able to supply any solution because they are identical now. But the initial logic of the profit margin works here. The larger the profit margin, the more that I want to produce that product. Okay. Now, of course, it turns out that this is actually a simple problem where there are some business approaches, intuitions about profit margins or we can create actually some margins that are similar to that. But basically, these are single performance measures on a system which looks very simple. Okay, this system looks very simple, but it turns out to be very complicated in the sense that it has a capacity limitation and it has a demand limitation. Okay, so we have limitations in both that will affect the outcome. So now we can see all the possible solutions with this simple problem. What happens if I increase the number of products? What happens if I increase the number of equipments that we use? What happens if I change the demand patterns? Okay, what happens if I define substitutable products? Okay, if you cannot find that product, you can buy the other one. Okay, there are many things that I can make this problem more complicated, and the solution of this problem is, of course, not as simple as selecting according to a single rule. You have to make sure that you encompass a number of different possibilities, scenarios, to find the optimal solution. Now, we're going to see how these type of very simple structured, linear structured problems can be solved when we use linear programming. Okay? And we're going to learn something about the solution, but basically it turns out that neither of the claims are absolutely going to be correct. Okay? We have to make sure that when you have complications like capacity constraints, when you have complications like demand upper bounds, life is not as simple as one might think. Okay? So we're going to see how to solve this problem. So this is an example of critical thinking. You can critically think about this problem, but still your knowledge is not sufficient to bring up a general solution. Okay? You were very good in obtaining solutions to the specific problems that I give, but I am talking about a more general solution, regardless the values of the profits, capacity usage, and so on. We have to have an approach to solve these type of problems. Okay? Because using intuition all the time is not going to lead us to the correct place, especially if the problem gets more complicated. So critical thinking, together with some techniques that you learn, is going to lead you to some point. Otherwise, it's not going to be sufficient in itself. Okay? But you always need that, definitely, because you are the person who is formulating this problem. So any questions on this? So we're going to see the solution of this in week 13 of the week before the course is out. So first week of May, actually, we will be talking about this problem. Yes?
Why do we use profit margin when our outcomes are same?
Okay, the outcomes are the same with respect to profit per capacity. But because in this problem, we have only two aspects of the problem, because it is a two-product problem. So it's either that or the other one. And that's the reason why when they are equal, when the way that they use capacity per unit of profit is the same, then the sole driver of the problem is the profit margin. So that's the reason why in that case optimality is obtained by the profit margin. So you fill the demand of the item with the largest profit margin first, and then the remaining one. Of course, all these solutions that we have been talking about are specific to these numbers. Hopefully, we're going to see a method that will solve, regardless of these numbers that we have here, that will solve these type of problems. So knowing that is going to be very important, of course, when you formulate these problems, because then you will not be using profit margin or any other thing without understanding what's going on. Okay, any other questions? Now, the final example, I think this is something that you can read from the text. The text mentions about the so-called Hawthorne experiments. This is very important when you consider improvements as we have been doing to it, in the course. Now, Hawthorne experiments are some experiments that were carried out in 1930s or 40s in a facility where people were doing a lot of operations manually. And what they did is, the claim was, if we upgrade the lighting, okay, the type of lighting which is used in the production, the efficiency of production will increase. So they will do the same thing faster if they see it better. So this is a very straightforward, actually, intuition. So what they did is they divided the whole factory floor into two. One part, well, they took two groups. One part operated in an environment which was better lighted. A lot of lighting was used, very, very high quality lighting. And then they had a control group where they kept the whole factory, the previous factory, as is. Okay? And what would we expect as a result of this? So they measured the efficiency of this group, and they measured the efficiency of the group that worked in the similar way as before. But of course, the people who were being measured knew that they were measured. So the expectation was that they were hoping that they will find this new lighting to be very efficient. So they would do all the investment, change the factory, increase lighting all over the factory as well. But it turns out that when they carried out a large number of experiments, this is the name of the plant actually, and they found out that actually the efficiency of the group which operated under standard conditions without changing was exactly the same as the other group, because they knew that they were being watched. So you can do a lot of things to increase efficiency. You can do a lot of things to increase the effectiveness of certain processes and so on. But unless you understand what's going on in the environment, a little bit beyond what you are doing, you might come up with much better ideas. So this is a very good example to show that. Of course, better lighting is going to increase the efficiency, but maybe giving some kind of motivating factors will also increase the efficiency. It's not always a new building or a new equipment and so on that will motivate people, because people are involved in such systems. Now, of course, this is a more traditional view of industrial engineering. In this department, you are going to see less of it. We have very little number of courses that will relate traditional industrial engineering to what we are doing in these days. We will be more towards mathematical modeling in this department. There are still some traditional departments left all around the world, but it is more for detailed technicians to do the rest of the work. There are a large number of things that have been done in the last 50 years for that part. We are going to see less of it, but I think it's an interesting example that you need to read in order to understand the idea of systems rather than individual efficiency. Okay, any questions? Okay, I'll see you next week.